Hello everyone. In this video, I have discussed the structure of metal carbonyl complexes. Various parameters which affect the structure in metal carbonyl complexes, like the nature of metal atom and carbonyl ligand, along with their number, are also discussed in detail. If you find my videos helpful, then please like and subscribe to my channel and don't forget to click on the bell icon to get new video update. Let's get started. We can describe the structure of metal carbon complexes with the help of valence bond theory. Before moving to discuss the structure of metal carbon complexes, first understand the concept of hybridization. It is a mixing of atomic orbitals belonging to the same atom having similar energy, so that redistribution of energy take place between them, resulting in the formation of new orbitals of equal energy and identical shape is known as hybridization. And the new orbitals are called hybrid orbital. For example, in acetylene, the 2s orbital of carbon combined with one of the filled 2p orbital of the same carbon to form 2sp hybrid orbitals. The lobes of these 2sp hybrid orbitals are opposite to each other. When these hybrid orbitals overlap with the sp hybrid orbital of other carbon and the 1s orbital of hydrogen, gives linear geometry of the acetylene molecule. Similarly, the sp2 hybrid orbital is obtained from the overlapping of 1s orbital and 2p orbitals of the same atom. Now let us have a quick look at the other hybrid orbitals. Okay, coming to the metal carbonyl complexes, we can classify them as mononuclear, binuclear and polynuclear carbonyl complexes. The first one is mononuclear carbonyl complexes. Three different geometries are possible in these mononuclear carbon complexes. Nickel tetracarbonyl and palladium tetracarbonyl have a tetrahedral geometry. Iron pentacarbonyl, ruthenium pentacarbonyl and osmium pentacarbonyl have a trigonal bipyramidal geometry, while the hexacarbonyl of vanadium, chromium and molybdenum along with tungsten have octahedral geometry. Okay, consider the first example of tetracarbonyl nickel. The atomic number of nickel is 28, so its valence electronic configuration in the ground state is 3d8 4s2 4p0. Now, since the carbonyl ligand is neutral, the valence electronic configuration of nickel in the excited state is 3d10 4s0 4p0. Then the vacant 4s and 4p orbitals are hybridized to produce sp3 hybrid orbitals. The HOMO of the carbonyl ligand then donate its sigma electron to empty sp3 hybrid orbitals of the nickel to form a sigma bond. Acceptance of 4 electrons pair by nickel in a zero oxidation state severely increase the electron density on the nickel atom. Thus, the nickel donate back some electron density from the filled d orbitals to the low-lying LUMO orbitals on the carbonyl molecule to form a pi bond. As the hybridization is sp3, the geometry of the complex is a tetrahedral. Moreover, there is no unpaired electron, so this complex is diamagnetic. The point group of this complex is tetrahedral. The atomic number of iron is 26, so its valence electronic configuration in the ground state is 3d6 4s2 4p0. Since the carbonyl ligand is neutral, the valence electronic configuration of iron in the excited state is 3d8 4s0 4p0. Then the vacant 4s and 4p orbitals and the d orbital which is vacant are hybridized to produce dsp3 hybrid orbitals. The HOMO of the carbonyl ligand then donates its sigma electron to empty dsp3 hybrid orbitals of the iron to form a sigma bond. Acceptance of 5 electrons pair by iron in a zero oxidation state severely increases the electron density on the iron atom. Thus, the iron donates back some electron density from the filled d orbitals to low-lying LUMO orbitals on the carbonyl molecule to form a pi bond. As the hybridization is dsp3, the geometry of this complex is trigonal bipyramidal. Since there is no unpaired electron, so this complex is diamagnetic and the point group is D3H. The atomic number of chromium in this is 24, so its valence electronic configuration in the ground state is 3d5 4s1 4p0. Since the carbonyl ligand is neutral, the valence electronic configuration of chromium in the excited state is 3d6 4s0 4p0. Then the vacant 4s and 4p orbitals and the 2d orbitals which are vacant are hybridized to give d2sp3 hybrid orbitals. The HOMO of the carbonyl ligand then donates a sigma electron to empty d2sp3 hybrid orbitals of the chromium to form a sigma bond. Acceptance of 6 electron pair by chromium in a zero oxidation state severely increase the electron density on the chromium atom. Thus, the chromium donates back some electron density from the filled d orbitals to the low-lying LUMO orbital on the carbonyl molecule to form a pi bond. As the hybridization is d2sp3, the geometry of this complex is octahedral. Moreover, there is no unpaired electrons, so this complex is diamagnetic and its point group is OH. The transitions metal with odd electron such as manganese, cobalt and copper cannot satisfy the effective atomic number rule in neutral condition. Thus, to stabilize and satisfy the effective atomic number rule, such metals in a neutral oxidation state form polynuclear metal carbonyl complexes. I have already discussed the effective atomic number rule in metal carbonyl complexes in previous video. I have given the hyperlink of this video on the effective atomic number rule in the description box. In dimanganese decacarbonyl, the atomic number of manganese is 25, so 50 electrons form the 2 manganese atom. Also, each carbonyl ligand will donate 2 electrons, so 20 electrons from 10 ligand. 2 electrons count from the manganese-manganese bond. Consequently, the effective atomic number of this complex is 72, that is 36 electrons per manganese atom. Thus, this complex follows effective atomic number rule and is stable. Likewise, manganese, the metal atom which with an even atomic number also form polynuclear carbonyl complexes to stabilize their complexes. For example, the iron atom can form 2 different types of polynuclear carbonyl. The number of metal-metal bonds in binuclear, trinuclear, tetranuclear and hexanuclear carbonyl complexes are 1, 3, 6 and 12. As you can see in the table that binuclear carbonyl complexes like dimanganese decacarbonyl, dicobalt octacarbonyl and diiron nonacarbonyl have 1 metal-metal bond. Tri-iron dodecacarbonyl has 2 metal-metal bonds. Tetracobalt dodecacarbonyl has 6 metal-metal bonds, while hexarhodium hexadecacarbonyl has 12 metal-metal bonds. The second category is binuclear carbonyl complexes. Binuclear carbonyl complexes of manganese, technetium and rhenium have octahedral geometry. Dicobalt octacarbonyl complexes has a trigonal bipyramidal geometry in the solution phase, while its complex is a slightly distorted octahedral geometry in a solid phase because of bridging carbonyl complexes ligand. Diiron nonacarbonyl has a slightly distorted octahedral geometry because of the bridging carbonyl ligand. Okay, consider the example of dimanganese decacarbonyl. The atomic number of manganese is 25, so its valence electronic configuration in the ground state is 3d5 4s2 4p0. Since the carbonyl ligand is neutral, the valence electronic configuration of manganese in the excited state is 3d7 4s0 4p0. Now, as mentioned earlier, having an odd atomic number, the manganese atom gets polymerized to stabilize its complex. In this complex, there are two manganese atoms, so number of electrons involved in one metal-metal bond will be 2. The 4s orbital, 4p orbitals and the d orbital with an odd electron are hybridized to produce d2sp3 hybrid orbitals. Thus, the d2sp3 hybrid orbital with an odd electron get paired with manganese-manganese bond formation. Each manganese atom accepts 5 pair of electrons from 5 carbonyl ligand in its 5 vacant d2sp3 orbitals. As the hybridization is d2sp3, the geometry of the complex is octahedral. Moreover, there is no unpaired electron, so this complex is diamagnetic. To avoid ligand-ligand repulsion, the MnCO5 units acquire staggered conformation. The point group of this complex is D4D. The structure of dicobalt octacarbonyl in the solid state has 2 bridging carbonyl ligand, whereas its structure in the solution like hexane has no bridging carbonyl ligand, and each cobalt has 4 terminal carbonyl ligand to form staggered conformation. In the FTIR spectra, dicobalt octacarbonyl in the solid state shows 2 stretching frequency at 2100 cm inverse and 1886-1857 cm inverse, which are correspond to terminal carbonyl and bridging carbonyl respectively. Whereas in a solution, it shows a band at 2000-2100 cm inverse, which is correspond to terminal carbonyl only. Let us consider the structure in the solution phase. The atomic number of cobalt is 27, so its valence electronic configuration in the ground state is 3d7 4s2 4p0. Since the carbonyl ligand is neutral, the valence electronic configuration of cobalt in the excited state is 3d9 4s0 4p0. In this complex, there are 2 cobalt atoms, so number of electrons involved in one cobalt-cobalt bond will be 2. The 4s orbital, 4p orbitals and the d orbital with an odd electron are hybridized to produce dsp3 hybrid orbital with an odd electron gets paired with cobalt-cobalt bond formation. Each cobalt atom accepts 4 pairs of an electron from 4 carbonyl ligand in its 4 vacant dsp3 hybrid orbital. As the hybridization is dsp3, the geometry of this complex will be trigonal bipyramidal. Moreover, there is no unpaired electron, so this complex is diamagnetic. To avoid ligand-ligand repulsion, the cobalt tetracarbonyl unit acquires staggered conformation. The point group of this complex is D3D. In the solid phase, there are 2 mu2 bridging carbonyl ligands. Here a singly occupied sp hybrid orbital of carbonyl overlaps with a singly occupied d2sp3 hybrid orbital of metal atom. The valence electronic configuration of cobalt in the excited state of this complex is 3d8 4s1 4p0. The 4s orbital, 4p orbitals and the d orbital with an odd electron are hybridized to give d2sp3 hybrid orbitals. One d2sp3 hybrid orbital with an odd electron gets paired with cobalt-cobalt bond formation. The other 2 d2sp3 hybrid orbital with an odd electron overlap with singly occupied sp hybrid orbital to form 2 mu2 bridging carbonyl. Each cobalt atom accepts 3 pair of an electron from 3 carbonyl ligand in its 3 vacant D2sp3 hybrid orbital. Moreover, there is no unpaired electron, so this complex is diamagnetic, and the point group of this complex is C2V. The ability of carbonyl to act as the bridging ligand decrease with an increase in the metal-metal internuclear distance. Thus, the relative stability of non-bridging carbonyl, that is terminal carbonyl, increases as the size increases down the group along a periodic table. Larger metal atoms tend to destabilize carbonyl bridge and show a greater preference for non-bridging structure. As you can see in the table, the binuclear complexes of iron and osmium shows 3 and 1 bridging carbonyl ligands because of difference in their atomic sizes. A similar behavior is also seen in their trinuclear complexes. Let us consider the example of di-iron nona-carbonyl. The atomic number of iron is 26, so its valence electronic configuration in the ground state is 3d6 4s2 4p0. In this complex, there are 3 mu2 bridging carbonyl ligands. So, valence electronic configuration of iron in the excited state is 3d7 4s1 4p0. The 4s orbital, 4p orbitals and the 3d orbitals with an odd electron are hybridized to produce d3sp3 hybrid orbital. One d3sp3 hybrid orbital with an odd electron gets paired with iron-iron bond formation. The other 3 d3sp3 hybrid orbitals with an odd electron overlap with singly occupied sp hybrid orbital to form 3 mu2 bridging carbonyl. Each iron atom accepts 2 pair of an electron from the 2 carbonyl ligand in its 2 vacant d3sp3 hybrid orbitals. Moreover, there is no unpaired electron, so this complex is diamagnetic, and the point group is D3H. The third category is the polynuclear carbonyl complexes. The trinuclear carbonyl complexes of iron has 2 mu2 bridging ligand, while the trinuclear carbonyl complexes of osmium and ruthenium have no bridging ligand. The tetranuclear carbonyl complexes of iridium has no bridging ligand, while the tetranuclear carbonyl complexes of cobalt and rhodium have 3 mu2 bridging ligand. The hexanuclear carbonyl complexes of cobalt and rhodium have 4 mu3 bridging ligands. Let us consider the example of triruthenium dodecacarbonyl. In this complex, there are 3 ruthenium atoms, so the number of electrons involved in 3 ruthenium bond will be 6. The atomic number of ruthenium is 44, so its valence electronic configuration, the excited state is 3d8 4s0 4p0. The 4s orbital, 4p orbitals and the 2d orbitals with an odd electron are hybridized to produce d2sp3 hybrid orbital. 2 d2sp3 hybrid orbital with an odd electrons get paired with ruthenium-ruthenium bond formation. Each metal accepts 2 pairs of electron from 4 pairs of electron from 4 carbonyl ligand in its 4 vacant d2sp3 hybrid orbitals. Moreover, there is no unpaired electron, so this complex is diamagnetic. The geometry of each metal atom is octahedral, while the point group of this complex in the solid phase is D3H. In the tri-iron dodecacarbonyl complex, we have 2 different types of iron. 2 iron undergoes D3sp3 hybridization and shared 2 mu2 bridging carbonyl. These 2 iron atoms accept 2 pairs of electron from the 3 carbonyl ligand in their 3 vacant D3sp3 hybrid orbital. The third iron undergoes D2sp3 hybridization and accept 4 pairs of electron from the 4 carbonyl ligand Moreover, the two hybrid orbital with an odd electron of each metal get paired with iron-iron bond formation. There is no unpaired electron, so this complex is also diamagnetic and the point group is C3V. In the tetrarhodium dodeca carbonyl complex, we have two different types of rhodium. In this complex, there are 4 rhodium atoms. So number of electron involved in 6 metal-metal bond will be 12. 3 rhodiums undergo D3sp3 hybridization and shared 3 mu2 bridging carbonyl. These 3 rhodium atoms accept 2 pairs of electron from 2 carbonyl ligand in their 2 vacant D3sp3 hybrid orbital. The 4th rhodium undergo D2sp3 hybridization and accept 2 pairs of electron from the 2 carbonyl ligand in their 2 vacant D2sp3 hybrid orbital. 3 hybrid orbital with an odd electron of each metal get paired with metal-metal bond formation. Moreover, there is no unpaired electron, so this complex is diamagnetic and the point group is C3V. In the tetra-iridium dodeca carbonyl complex, there are 4 iridium atoms, so the number of electron involved in 6 metal-metal bond will be 12. All the 4 iridium undergo D2sp3 hybridization and accept 3 pairs of an electron from 3 carbonyl ligand in their 3 vacant D2sp3 hybrid orbitals. 3 hybrid orbital with an odd electron of each metal get paired with to give metal-metal bond formation. Since there is no unpaired electron, this complex is diamagnetic and the geometry is tetrahedral and the point group is also tetrahedral, TD. In the hexarhodium hexadeca carbonyl complex, there are 6 rhodium atom, so number of electron involved in this 6 metal-metal bond formation will be 12. All the 6 rhodium atoms undergo D2sp3 hybridization and accept 2 pairs of electron from the 2 carbonyl ligand in their 2 vacant D2sp3 hybrid orbitals. 3 hybrid orbital with an odd electron of each metal get paired with rhodium-rhodium bond formation. The other odd electron of each rhodium atoms from D2sp3 hybrid orbital shared with 4 mu3 bridging carbonyl. Moreover, there is no unpaired electron, so this complex is diamagnetic and the point group of this complex is OH. Now I end this video here. Thanks for watching. Please like and subscribe to my channel. See you in the next video of this series.